Hello, guys. Welcome back to Maison African Motives, still on engineering science. And for here, we are going to be focusing with statics from the question paper of November 2020. Like I said, I'm going to work with this question paper because it's more of our November 2022 question paper that we had. And it's very, very important that we see some of these parts so that we see how are we supposed to attempt this typical question, just like that question, but only different values that you're given. All right, so you're given a light horizontal beam on question number 4, which is referred to as A, B, C, D, E, with A on the left-hand side, 13 meters long. So the beam is the one that is 13 meters long, and it is supported by two points, which is A and D. So the A and D representing the supports. All right, and okay, let's just save this information at once so that we can just have our sketch. This is first part. You're going to sketch this and that. All right, so you're given A and D. These are supports. So you're given A and D as our supports in this case. And also the other important thing is that A is direct on the left hand side. All right, so this brings us to the diagram. Let's just save our diagram because this can take us a lot of information out trying to do this and that. So I'm just going to present this. All right, so let me just have my ruler here, present our horizontal line. I think the black one is good for this line. All right, so this is what we're going to have from our line. Then let's check the first part. We're given that A is a support. So we've got the point A direct at the end here. So this is where we are going to have our point A. Okay, let me just try to increase so that we can have this peacefully. All right, so we have got our A at the end here. That is where we have our A, which is a support. So in this case, we can just write this A. All right, so that's our A, a support. And this whole part is actually 13 meters from this point up to the end. It's actually 13 meters. We shall talk about this later on. I shall talk about this later on. Okay, so this part we are now given that between these points that we have at B, 6 meters from A, so take note, it's 6 meters from A, there is a point load of 10 kilonewton, that is at B, which is 6 meters from the point A, meaning to say after A here, 6 meters to this side, we are going to have another part which is referred to as B, which is also a point load. So this is a point load. This is the first point load actually at B. That is at a distance from A of 6 meters in this case. So take note, we are given a distance here of 6 meters in between. So this is 6 meters. And our point load, this one is at 10 kilonewton. That is a 10 kilonewton. All right. So let's move on to the other part and see what you're given. After that, at C, that is at this point here at C, we are now given 3 meters from B. There is a point load 15 kilonewton. All right. That is at C, which is 3 meters from what? From B. So this is our B here. Remember that this represents our B. All right, so let me just remove this part here. So this whole part is 13 meters, remember? So here I'm just gonna put this direct to say this is my B. Direct at this point, this is my B. So remember, I told that there is from B, there's got 3 meters from this point to the point C. So there's 3 meters in between. We are going to have a point load there, which is referred to as C. So this is going to be a point load that is facing down at C. All right, so this is what you're going to have at the end. So this is going to be our point C. Let me put this away. Okay, so this is my point C here, having a point load at C of 15 kilonewton. So you're given this is 15 kilonewton. Okay, so that's what we had. And if we move from the point C, we are now given this, that there is a uniform distributed load of 4 kilonewton per meter between A and B. Between A and B, that's 4 kilonewton per meter. So between these 2 points, A and B, we are going to have a distributed load here. So there is a distributed load of 4 kilonewton per meter. That is affecting for these 6 meters. Okay, then from there, we are given that D is 2 meters from C, and D represents what? A support. Remember, we said D is a support. So there's a support that is 2 meters from C. So this is from C. We're going to have, take out of this, we are going to take 2 meters. So how many meters have we covered if we say our D is at this point here? So this is where we have our D. Remember, D is a support. So we're going to have our support here, which is our D. All right. So, but remember, this is a light horizontal beam, which is represented as A, B, C, D up to point E. So what do we have now? If this is 2 meters, remember, all in all, this was 13 meters. This beam was 13 meters. So this is 6 plus 3, which is 9. 9 plus 2, which is 11. So we have covered 11 meters so far from A to point D. This is 11 meters that we have covered in this case. All right. So let me put it this way. From the point A to the point D, so far we have covered 11 meters between these 2 points. So what's going to happen with the remaining 2 meters in this case? What's going to happen with the remaining 2 meters? That is from the point D to E, because this is 11 meters that we have taken. But remember, it is supposed to be 13 meters all in all. So 13 minus 11, meaning to say we are going to remain with 2 meters. That is going to give us the point which is at E. So at E, we do not have anything. We just have a distance between D and E, which is 2 meters, only that. All right, so this information was actually enough. This is the diagram that you're going to have at the end. So we can actually remove this part. Okay, up to this. So this can be your diagram, just like that. Okay, so the question was for you to have the diagram so you can present in this way. All right, so this is actually enough for us. So this is from this point to this point. This is 2 meters. Remember, a distributed load between A and B for 6 meters or 4 kilonewton per meter and so forth. All right, so that was our question 4.1. Let's move on to question 4.2. In this case, we are now asked to calculate the reaction of the supports at point A and D, and also to test your answers after that, and that is 5 marks for that. All right, so let's see our reactions. That is at A and D. So we are going to also start with the first part, taking moments at A. So in this case, I'm going to consider moments about A. So taking moments about A in this case. Okay, so about A, what do we have? If we are to consider here, this is our A. Okay, so D is the major important part that we are supposed to calculate, which is moving this direction. That is like this, which is an anti-clockwise direction. So this is moving in the anti-clockwise, whereas the 10 kilonewton is moving back to this point, 15 kilonewton moving back to this point, which is a clockwise. So this is moving in the clockwise, this is in the clockwise. But remember that there is a distributed load of 4 kilonewton per 6 meters. So we are going to multiply 4 by 6, which is going to be 24 kilonewton. So this, we can just have it as a point load now of 24 kilonewton from 4 times 6. Now separated between the first 3 meters and the last 3 meters, because this is taken in between. So if you divide 6 by 2, this is going to be 3 meters. This is going to be 3 meters. Okay. And this moves in the clockwise. So we've got clockwise, clockwise, while D is in the anti-clockwise. So taking our moments about A, we are going to have the sum of the anti-clockwise moments being equal to the sum of the clockwise moments. So that's D back to A, which is a distance of 11, 4 times distance. So it's D times 11, which is the distance. So D times 11 is equivalent to the clockwise. So we've got 24 back to A here. This is 24 times the distance of 3 meters. So that one is going to be 24 times 3. We move on. So this is part that I said you must correct what we had on the November 2022 question paper, the one that I did. It was actually an error from the memo. So that's why I'm bringing these questions, so that you see that these are actually errors that you had there from that November 2022 question paper. Anyways, let's see what we're going to have here. From B back to A here, that is a distance of 6 meters. So we are going to have 10 times 6 back to the point A. C back to A, there's a distance of from this part 6 plus 3, which is 9. So this is going to be 15 times 9. So all these, they are in the clockwise. And E has got nothing, that's a 0 there. So there's nothing for us to work with that E. So that's D times 11, which is going to give us 11D is equal to whatever that you're going to combine on the right-hand side. Here we are going to obtain 267. Divide by 11 both sides. We are going to obtain the value of D in kilo Newton, just like the other part that we had. All right, so our D in this case is going to give us something like 24,273 kilonewton, like this. Okay, so that's our point. That's our force. The point load, the support that we have a D. Okay, so D is a support, and we got this one. So I'm just gonna write here a D. This is 24,273 kilonewton, like that. Okay, so using the same information or the same idea, we can calculate the moments. We can calculate the reaction now at A, because this now is going to change. This is no longer clockwise, so this part I'm going to remove this. Okay, so now referring to moments about D, so that we can calculate the support A. This is what you're going to have. All right, so let me just put it this way. So this time we are going to consider moments about D. So if we consider moments about D, A is moving this way to D. This is the direction of A. Take note, the direction of A is this way back to D, which is this way, like this. That is a clockwise. So this is moving in the clockwise. But if we consider the other forces, we have got this 15 kilonewton back to D, that is anti-clockwise. Remember, this is anti-clockwise. Also 10, this is anti-clockwise. 24, this is also anti-clockwise. So this is anti-clockwise, this is anti-clockwise, this is anti-clockwise. Okay, so meaning to say we are going to have only one clockwise from A to D. So the sum of the clockwise moments should be equal to the sum of the anti-clockwise moments, that is from A to D. That's your clockwise. So force times distance between A and D, we've got 11 meters there. So it's going to be A times 11 equal to the anti-clockwise. So you're going to start with the first one just near to D, which is the 15. So it's 15 back to D. There's a difference of 2 meters, force times distance. So it's 15 times 2. So this is going to be 15 by 2. All right, so let me just try to put this way up. All right, so here I'm going to have 15 times 2 plus, I'm still having another anti-clockwise of 10 kilonewton back to D. So this is 2 meters plus 3, which is 5. So it's 10 times 5. So this is going to be 10 times 5. Plus, we still have another anti-clockwise of 24. It's now a point load because we've treated this now as a point load of 24. So it's 24 times the distance back to D, which is 2 plus 3, that's 5, plus 3 from this point, that is where we are calculating, we are adding these 3. So it's 5 plus 3, which is 8. So this is going to be 24 times 8. So avoid errors there. All right, 8 times 11, this is 11A equal to, if you simplify everything there, we are going to obtain 272. So if we divide by 11 both sides, this is going to give us the exact value of A, which in this case, we are going to obtain 24,727 in kilonewton, like that. All right, so this is our A in this case. All right, so with this A that we got, we are done. All right, we are done because these are the supports. So I'm just going to write this, my A at this point here. So that's 24 here. So this going to be we say 20, not 20, that's 24. So these values are actually almost the same, 24,727 kilonewton. All right, so these are the values that you're going to obtain in this case for the supports. All right, so that was our question. And also we are asked to test our answers. So in this case, we can just test our answers. Okay, let me just increase this one. So let us just test our answers here and see what we gonna obtain. Are these going to be the same because we are supposed to obtain the same thing? Okay, how do we test our answers? We can apply the condition of upward forces must be equal to the downward forces. So this is the best way that we can actually, okay, let me just use this space. I think I'm now taking a lot of your time now trying to erase this. Let me just use this part. All right, so let's just test our answers here. All right, so let's test. So we are going to test using the concept of upward forces. They must be equal to the sum of the downward forces in this case. So the upward forces, we've got A and D. So A is going up with 24,727 plus D is going up with 24,273. So this is supposed to give us all the downward forces. We have got this now as 24 from the distributed load. Now from this uniformly distributed, now it's going to be 24. We have got the 10, which is also pointing down. So we've got 10 plus 15, which is also pointing down. So we're going to add the 15 there. So this is going to give us the sum of the upward forces here of 49 kilonewtons. So this is going to give us 49 kilonewton equal to also 49 kilonewton. These values must be exactly equal, not to obtain a decimal from another one is giving you a whole number. No, it's not supposed to be like that. As long you've done your calculations properly with the degree of accuracy that you're given, the answers must be directly equal. Not to say this is going to be the same, but they are not the same. No, it's supposed to be equal exactly like this. That is what you're supposed to do. Okay, so the other part of the question, so this is actually done. We move on to the other part of the question, which is 4.3, where we are now asked to draw a shear force diagram for this information, showing all the main values on the diagram, and that is 4 marks for that. Okay, so I'm going to have my 4.3 just down here on this diagram. All right, so that is going to be easiest way for us here if we have this just down here. So I'm just going to shift. All right, so let me just have my points done. So this is what I'm gonna have here. Okay, so I'm just gonna have my points like I extend from A, this is the major point, B, the major point, C, D, and E. Okay, so remember on your shear force diagram, guys, what is very, very, very important is for you to understand the points that you're going to consider with the scale that you're going to have. So in this case, I'm not having any scale, any important scale that I'm going to apply. I'm just going to show you the major points, but you're supposed to work them with the scale that you have. So this, I'm going to start at 0 kilonewton at this point here. But let's see what's happening at A. At the beginning, we are having a support. At the beginning here, there's a support which is going up. Remember, a support is always a positive. So at 0, we are going to add the support. We are at 0, so we're going to add the support, which is at 24,727. Anything that is positive possesses a positive. So if you add this, there's nothing that's going to change. It is going to remain as 24,727. So at 24,727, that's where we are supposed to mark your point. So let's say approximately my point is here. So this is where I'm going to join straight. It's a support goes up straight. All right, so that's our shear force diagram. So the support is drawn vertically going up like this. All right, so we've got our support here at 24,727. That's 727 kilonewton, 727 kilonewton like this. Okay, then let's check what is happening between the points A and B. Between these two, these are the major points. There is a distributed load, if you are to check here, of 4 kilonewton per meter, affecting for 6 meters. So we multiplied the 4 and the 6, and we got 24. So we're going to subtract from the 24,727, where we are at this point. We subtract, because it's on top, it's going down, so it's a negative. So we subtract 24, or we subtract 4 times 6, which is the 4 kilonewton times the distance from A to B, which is 6 meters. So this is going to give us 0,727. That's 0,727. So that's 0,27. It's above the line. in the positive, so it's just above. So according to your scale, maybe approximately 0.27 is at this point. So you join, this is going to give us a slanted line like this. A distributed load always gives us a slanted line like that. Okay, so if I join these 2 points, let's see what you're gonna have. If I join these two, I'm gonna have a slanted line automatically. That's what happens here. So this is what you're going to have from this point up to this point. That's B, that's A up to C in this case. All right. So with this information, guys, all right, I have taken this ruler down. Okay, let me just write 9. Okay, it's no longer possible. Let me just bring my ruler back, guys. Okay, they have stolen or they've taken this ruler, these guys. Okay, so this is what is important, guys, to say that the points are supposed to be properly presented. Okay, so this point here, we said we are at 0, that's 0, 0.727 kilonewton. That's at B. Okay, at B, let's check what we have at B. At B, after this movement, at B, there's a point load going down, which is a negative, so we're going to subtract 10. So at 0.27, at this point where we are at this 0.27 here, we are going to subtract at 0.727. We are going to subtract 10. That is going down, so you subtract 10. It's a point load, so it goes down straight in a vertical manner. So this is going to give us a negative. That's negative 9.273 kilonewton. So this is going to go down to the negative. So maybe approximately according to your scale, this is where we've got our negative 9 at this point. So you have to join direct to that point. This is a vertical line that we are talking about. So here we are going to join a vertical line from 0 to negative, the value that we have there at this point. Okay, so this is at a negative 9.273 kilonewton at this point. All right, so let's check the other part and see what we have. All right, that's B. Now we move on from B to C. How are we going to move from B to C? There is nothing. We do not have a distributed load like what we had from A to B. So this we move straight a horizontal between A, B, and C. So we're going to move straight. There is nothing that is affecting. So this one, we move straight in a horizontal. So this is going straight in a horizontal, meaning to say we are still at the same value of negative 9.273. We are still at the same point at negative 9.273 kilonewton at this point. Okay, that's at C. Now at C, what do we have? Direct at C. If we reach the point C, we are going to notice that at C, after this movement, there is a point load going down. That's a negative. So we're going to subtract, just like what we did for this 10, we subtract 15. So at this value, where we are at negative 9, this value that we have at negative 9.273, we are going to subtract our point load at C. And at C, there is a point load of 15 kilonewton. So you subtract that one. All right, so minus 15, what am I going to obtain? I'm going to obtain negative 24.273. So this is a point load. So it goes down vertically, down straight to negative 24, so according to your scale, maybe this is the point, you mark it according to your scale. So 24.273, maybe it's somewhere here. So here I'm just gonna join vertically straight to that point. We are still on B, so it goes down straight like this. Okay, so that's it between these 2 points. All right, let's check what we have from C to D. All right, between C and D, there is nothing, just like between B and C. So we're going to move straight a horizontal line to join from these 2 points. That is between C and D. So here we do not have anything. So it's going to be horizontally joined straight, meaning to say we are still at negative 24.272. We are still at this value here. We are still at this value of negative 24.273. That's where we are still at kilonewton. All right. So from this value now, we are at point D. Straight here, we go straight to point D. D is representing a support. And a support, it's a positive. It is going up. It's a positive, just like A. So we are going to add, and we represent with a vertical line going up. That's a support. So we're going to add where we are going to add the support at D 24,273. At minus 24, 273 where we are, if we add 24,273, we are going to obtain 0 kilonewton. So this is going straight to the 0 point, which is to the horizontal line at this point. Remember, our 0 is from this horizontal, so it is going straight to the horizontal. That's a straight vertical line in this case. So here we are going to draw a straight vertical line up to that point. All right, so that is up to this point, a straight vertical line up to 0. So we have closed the figure of, or we have closed our diagram at 0, meaning to say this is actually in equilibrium. Okay, so that is what you're going to have in this case. And if you have to check what is happening at E, we do not have anything. We are already done. At E, we do not have a force. We do not, and our diagram is already closed. So we can just indicate that our E is at this point, but there's nothing that we have there. So just indicate E. So that's what we have. So that was our at D, at C, at B, and at A. So just like that. Okay, so these are the major parts that you're going to have on your diagram, or the major points that you're supposed to have on your diagram in this case. All right, so let's consider another question. 4.4. Calculate the bending moments at B and C. That is the bending moments in this case at B and C. And we are given 2 marks for that. All right. So that's 4.4. Bending moments, we can just use our diagram here on top. So I'm just going to work them here. We do not have a lot there. All right. So the bending moments, remember, okay, let me just remove this part. It's not going to affect us in this case. Okay, so let me just have it this way. Okay, so I'm just going to have this as my 4.4. So remember that the bending moments, we are going to start with B. The bending moments, we are actually talking about the force times distance taken from the point that you are referring as your reference point. In this case, we are referring to B. So if you are to check at B here, if I am to take from the left-hand side, if I'm taking from the left-hand side here, I've got 2 forces that I'm going to consider from B. That is A to B, and that 24 kilonewton here back to B. But take note, everything that goes up carries a positive, everything going down carries a negative, and it's force times distance. So this is going to be positive. A is going up, that is a positive 24,727 times the distance to the point B. So from A to B, there's a distance here of 6 meters. So we multiply by 6, okay? Plus, if you consider 24 kilonewton back to B, there's a distance of 3 meters, and this is a negative because it is going down. So that's negative 24 times the distance back to B, which is 3 meters like this. So if we combine everything, that's our bending moment at B is going to give us 76,362. That is kilonewton meter in this case. This is in kilonewton, force times distance. So it's kilonewton meter. All right. So this, we took this from the left side. So from the left-hand side. All right. So that's it. We move on to another part, that is the bending moment at C. So we're going to have the bending moment at C. And I told you guys from the November 2022 question that we did that it's easier for you to consider the bending moment at C working from D, because we just have D and that one at C. There's a direct force here without a distance, because there's no distance between this and C. So you can just consider from what? From the right-hand side. Instead of you working from the left-hand side, yes, you can obtain the same answer, but from the right-hand side, we've got force times distance. It's a positive, it's going up. So it's positive 24,273, that is this one, times the distance between D and C. We are considering force to C, which is a distance of 2 meters. Then plus this one of 15 is going down. It's a negative 15. But what is the distance between this and C? There is no distance between this point because it's at the point C. So this one is going to be times 0. So there's nothing there. So this is going to give us 48 comma, so this is going to be 48. Okay, let me just change this one. Okay, so that's 48 comma 546 kilonewton meter. All right, so that's it, guys. We've got the bending moment at B here, the bending moment at C, so that is 2 marks for that. And the last part of the question, which is on question 4.5, was now to draw a neat bending moment diagram and show all the main values on the diagram. And the main values we've already calculated. The main values are the ones that we have already calculated here. That is, we consider B and C, and the other values, that is from A, B, from A, and so forth. So at A, what do we have? Because we calculated at B and we calculated at C. So this is what we got on our diagram here. Okay, I'm here on my diagram here. So we considered the point B, the point C. What do we have at A? At A, this is the end point. There is a 0 there. D is an end point. Yes, there is E, there is nothing there. So meaning to say D is at 0, A is at 0. So meaning to say our bending moment, remember, when we are dealing with a bending moment, you need to know how to present on that diagram. Okay, so let's present it this way. 4.5, I'm gonna have it here. All right, so let's see what you're gonna have. Okay, let me just use another marker here. Okay, so 4.5, we need the bending moment diagram. So in this case, I'm just gonna have my horizontal line. Okay, let me just, yeah, where's that ruler? Okay, let me just present this with a ruler so that we can just have a proper diagram. All right, just a horizontal line. Okay, this is enough. Okay, this is enough. Okay, so starting at 0, which is at A, so at A is actually at 0. What do we have between A and B? Yes, we've got a bending moment at B, but if you check between these points, there is a distributed load that we are given in between here, which is going to be presented in form of a semicircular, just like a curve like this for a distributed load. All right, so you're going to represent with a curve. So you're going to represent a curve from A up to B with a curve like this. All right, so let's say this is where we have our B, which is at 76, 362 kilonewton meter. All right, that's kilonewton, not kilometer here, kilonewton meter. All right, so that's what you're gonna have at B. Then at C, we are given the bending moment less than the one at B. So here, we do not have a distributed load. So what you're gonna do is you represent with a diagonal line. The same way you were doing on the shear force diagram. Remember, on the shear force diagram, you use a diagonal line like a slanted line like this to represent a distributed load. But this is a normal presentation on bending moments where there is no distributed load. Where there's a distributed load, it's a curve. All right, it's just a curve like. Okay, so this you use a normal diagonal line. So we are going to draw from B up to C at 48, at C, that is at 48, 546. So we are going to draw this here, a straight line just here at 48, 546 kilonewton meter. Then at the end, we have got D. Remember, D is that's like a starting point because there's nothing at E. So this is going to be 0. So D is going to be at 0, meaning to say D is at ground. So our D is going to be taken at ground from this point to this point at ground, that is at 0 kilonewton meter. Then we have got our point E. So this is like our D, our C, our B here, and our A from the starting point. Okay, so bending moment, guys, you have to be very careful. Work with the information that you're given. Some other questions they might ask in a different manner, and you need to work with extra calculations on that consideration. So you just need to work with more question papers. That's what you're going to have as we move on as a family. But for now, that's it, guys, from Maison African Motives on engineering science and 4 till we meet again.